Welcome. Welcome to this session of pharmaceutical analysis. Today we are going to understand the specific quantities and concentration. This is in continuation to our previous lecture. In the previous lecture, we discussed about the molarity, which is one of the way of expressing the concentration. We have also discussed the percentage weight by weight, percentage weight by volume, and percentage volume by volume. Very important parameter also we discussed about the to measure the very low concentration is parts per million and parts per billion. Now moving to the next expression of the concentration, just look at some of these expressions which are used for the concentration other than the parts per billion, or the percentage weight. So the first we discussed about in the previous section, we discussed about the molarity, which is the number of moles of solute per liter of solution, but that was with regard to the chemical formula of the compound. But what happens when we have ionic compound? When we have ionic compound, then we calculate or we express the concentration in terms of formality. It is the number of moles of solute per liter of solution with regardless to the chemical formula of the compound. So when a compound is ionic in nature and it is dissolved in a solution, so or per liter of the solution, it is termed as the formality. And it is not used for the molecules or the compounds. For the compound we use the molarity, and for the ionic compounds we use the formality. Now the next is molality. This molality is the number of moles of the solute in 1 kg of the solution by weight. It is by weight. Solution we are taking the weight of the solution. So this is the number of moles of solute in 1 kg of solution. Now the next very important expression is the normality. We will discuss in this session that what is normality in detail. So this is the number of the equivalents. We will learn that what is this equivalent of solute in 1 liter of solution. What is equivalent weight? The weight of one equivalent compound. This is just a very basic definition. Now let's discuss this normality or some equivalent weight in detail. So normality. This normality is very similar to the molarity, except that it is utilized as a quantity of chemical called the equivalent rather than the mole. It is very similar to the molarity, but it is different to utilize. It utilizes the quantity of chemical called the equivalent rather than the moles. In the molarity we use the number of moles. Here we use the equivalent. Now so it is defined as the number of equivalents per liter rather than the number of moles per liter. So this is the difference between the normality and the molarity. Molarity is number of moles per liter and the normality is number of equivalents per liter. So it is dependent on the specific chemistry of the analysis. This equivalent. It may be calculated by dividing the equivalent of solute by liter of a solution in which the number of equivalent is dissolved. We will understand that what is this equivalent. So for example, if there are 2 equivalents dissolved per liter, a solution would be referred to as 2 normal or 2N. If there are 2 equivalents dissolved in per liter, so we say that a solution would be referred as 2 normal or 2N when 2 equivalents are dissolved. When it is 1 equivalent, it is 1n. When it is 3 equivalent, it is 3n. So the equivalent is either the same as the mole, it can be mole, number of moles, it can be same as number of moles, but it can be different than number of moles. So it can be same as mole, it can be some fraction of mole, depending on the reaction which is involved. So the equivalent weight or the weight of one equivalent is either same as the formula weight, or it may be some fraction of the formula weight. We will discuss, you will understand what this means, what I am talking about when we give the examples. So normality is either the same as molarity or some multiple of molarity. Molarity, it is similar to molarity or some multiple of the molarity. So for this, we have to understand the acid-base neutralization reaction. Now, you can see that this is equivalent weight of an acid and equivalent weight of a base. So equivalent weight of an acid is in an acid-base neutralization reaction. This equivalent weight can be in the oxidation reduction reaction of a oxidizing agent, of a reducing agent, but here we are talking about of an acid in acid-base neutralization reaction. So this equivalent weight of an acid and acid-base neutralization reaction is defined as the formula weight divided by number of hydrogen lost per formula of the acid in the reaction. So when during the reaction the number of hydrogen are lost per formula of acid in the reaction, then the formula which becomes, it is the equivalent weight. Again I am repeating, this equivalent weight of an acid is in an acid-base neutralization reaction is defined as the formula weight divided by number of hydrogen lost per formula of acid in the reaction. So acid may lose one or more hydrogen per formula when reacting with a base. See the example that the hydrochloric acid HCl, when it reacts with sodium hydroxide, it gives sodium chloride plus water. So now the hydrochloric acid, because we are talking about equivalent weight of an acid, so hydrochloric acid is losing one hydrogen. It is one equivalent. Now the next is sulfuric acid. When it reacts with excessive of sodium hydroxide, it gives sodium sulfate plus water. Here two hydrogens are lost by the sulfuric acid. So that means this is 2 equivalent weight of the sulfuric acid. So while we are calculating the equivalent weight, we have to divide it by 2. So now if we are calculating the normality by the HCl in the reaction of HCl plus NaOH, because one hydrogen has been lost, so we will just take the example of take one equivalent. That means we will just take as a molecular mass of this HCl. While in the H2SO4, this is divided by 2 because the molecular weight divided by 2 because there are 2 hydrogens which are lost by the hydrogen. That is known as the equivalent weight. So equivalent weight of HCl is same as its formula weight, and the equivalent weight of H2SO4 is the half the formula weight. So the equivalent weight is analogous to the formula weight in our molarity. The next is equivalent weight of a base in an acid-base neutralization reaction. Again I am saying that the equivalent weight we are calculating here in the acid-base neutralization. This is the reaction for acid and base. We can also calculate the equivalent weight in oxidation reaction, reduction reaction or redox reaction, right? So here equivalent weight of a base in an acid-base neutralization reaction. So it is defined as the formula weight divided by the number of hydrogen accepted. equivalent weight of the base, in equivalent weight of the base of acid, there is a number of hydrogen loosed, right, which is replaced. Here the number of hydrogen accepted per formula of the base in the reaction. So now this definition is based on the actually Bronsted-Lowry concept of the base, which is a compound that accept the hydrogen when it reacts with an acid, which is the Bronsted-Lowry concept of the base. So thus we can say that all hydroxide as well as the carbonate, ammonia, etc. are the Bronsted-Lowry base and accept the hydrogen when reacting with an acid. So base may accept one or more hydrogen per formula. So when reacting with an acid, they may accept one or more hydrogen. In both reaction above, which is of the acid, there is the sodium hydroxide we have used in the equivalent weight of an acid. So there is a sodium hydroxide which is accepting one hydrogen per formula unit. However, there are a number of bases who do not have the OH. Then we have to consider the hydrogen accepted per formula. So just like, see, the sodium carbonate, here is an example of sodium carbonate, is capable of accepting either one or two hydrogen per formula. In this case, this is the base, sodium carbonate is the base, and it is capable of accepting one hydrogen as well as two hydrogen. So just like in the first, sodium carbonate, when it reacts with the hydrochloric acid, it gives the sodium chloride plus sodium bicarbonate. Here the sodium carbonate is accepted one hydrogen. So sodium carbonate accepted one hydrogen. In the next reaction, sodium carbonate, when it is reacted with excessive hydrochloric acid, it forms 2 more of the sodium chloride plus carbonic acid. Here 2 hydrogen are accepted by the sodium carbonate, that converted into the carbonic acid H2CO3, and sodium goes to with the chlorine. So the equivalent weight of sodium carbonate may be equal to either the formula weight divided by 1, because the sodium carbonate total weight of the molecular weight of sodium carbonate, for example, is 105.99. So in the first case it is 1. The normality, we will just, how can we calculate it? We just take 104 is 105 and or 106 is the gram per equivalent weight of the sodium carbonate. So as in the first reaction, if the first reaction goes, it is a base react with the acid, right, and we are going to calculate the normality. So for this, because it accepts only one hydrogen, then it will be divided by 1. So if it is divided by 1, it will be the same. So 105 or 106 in 1 liter, that will give the normality. You will say that this is the same as the molarity, right? You are at this part when there is an equivalent weight is 1. So then it is the molarity and normality are both at the same concentration. While when there is an equivalent weight are different, that means other than the 1 is 2 or 3 or 4, then in those cases the weight, molecular weight, is divided by 2, 3 and 4. That gives the equivalent weight, and that will dissolve in 1 liter of the solution. That gives the normality. In that cases where the equivalent weight is 2, 3 and 4, right, where there are number of hydrogens are more than 1, that is 2, 3 and 4, then it will be different than the molarity. As I said, it will be a multiple of the molarity. So normality can be same as with the molarity and also the multiple of molarity. Now moving to the next is gram equivalent. We are talking about this gram equivalent. This gram equivalent, they are of basically 2 types. Actually, this is the part of equivalent. So there are two parts. One is the gram equivalent and second is equivalent weight. So one is known as, broadly known as, the gram equivalent weight, GEW, and second is EW, that is equivalent weight. We will discuss in detail in the coming lectures. But as of now, this gram equivalent weight, GEW, it is the weight in grams that is chemically equivalent to 1 gram atom of the hydrogen. The weight in gram that is chemically equivalent to 1 gram atom of the hydrogen. So it is also sometimes generally known as gram equivalent, and this gram equivalent weight has two distinct definitions. One is for the neutralization and second is for the oxidation reduction reaction. Let me remind you that we are talking about the concentration expression. And while we are working, we are making this preparation in terms of the normality. We are measuring the concentration in terms of normality. Then we have to consider all these points, the gram equivalent. Now, what is equivalent weight? Equivalent weight is the weight which loses electron equivalent to the 1 Faraday. And how much 1 Faraday is? 1 Faraday is 96,500 Coulomb. Actually, this may be calculated by dividing the gram molecular weight by the number of electrons which are lost by each molecule. We will discuss them in detail in the next lecture. But so these equivalent weight, they are the equivalent weight of an acid. They are maybe equivalent weight of a base in a neutralization reaction. It may be equivalent weight of the reducing agent. It may be equivalent weight of oxidizing agent. So this is all for today. In the next session, we will discuss or understand the gram equivalent in detail. Till then, thank you.